Okay, this video is going to be a brief description of what imaginary numbers are and how to express them when they arise. Um, so, to answer real quick, the imaginary number comes from the imaginary unit, the square root of -1, right? This is the imaginary unit. I'll just write that for short. Okay, so the imaginary unit is just the square root of -1, and it arises the first time that you try to take the square root of some number, right? So, for example, if I solve this equation, this would be x squared is equal to the square root, not the square root, not yet, is equal to -1, and then we take the square root. So x is equal to plus or minus the square root of -1. And mathematicians got tired of seeing this and being like, oh, well, we just can't do it. And they started just referring to it as the imaginary unit. And then, well, it turns out, so when you've got more complicated examples, so like let's say we solve this one, right? That's going to end up being x is equal to plus or minus the square root of -25. A little bit different, right? I can't just say that this is, so this one over here I know is plus or minus I, right? This guy here, though, is not so simple, right? But we know how to factor radicals. I can split this into just the square root of 25 being multiplied by the square root of -1, right? And I can just say this is plus or minus 5i, right? So there is where it arises the need to have something to fill in for those quote unquote non-real answers that we get that arise whenever we take the square root of a negative number. And it's not even from that. I don't think that imaginary numbers originated from in the first place, but we'll get to that. Not from that like example exactly anyway. So here we've got some examples of imaginary numbers that we're going to get from simplifying these radicals. So this one, pretty straightforward, right? This is just the square root of 9 times the square root of -1. In other words, 3i. This guy here, 17 is not a perfect square, and I can't factor it. It's prime, so this guy here is just going to end up being square root of 17i, right? And the correct way to express them, by the way, is in the form bi. So bi, bi. You get the idea. Okay, let's look at another one. So square root of 75, this one is factorable. So I can say that this is the square root of 25 times the square root of 3 times the square root of -1. 25 times 3 gives me the 75. 25 is a perfect square, right? So I can simplify this into 5 square root of 3 times I, or bi. And then we just keep going with this. I can factor the square root of 12, right? I can say this is the square root of 4 times the square root of 3 times the square root of -1, or just 2 square root of 3i. And I always like, so this b right here is a real number, right? And this is the imaginary component. This is the imaginary unit, right? So I always like to separate them with parentheses like I've been doing here. You'll also see sometimes, maybe they'll write 2i square root of 3. That drives me insane, but that's also considered correct. If you want to express it that way, though, I mean, by all means. And here, this is also factorable. I can do square root of 25 times the square root of 5. 25 times 5 gives me that 150. Again, we're always thinking of what are some perfect squares I can factor out. And then, of course, times the imaginary unit. And we end up with 5 square root of 5i. Okay, that does it for this video. That's what imaginary numbers are. If you're curious what I was talking about as far as like where they came from, this Italian mathematician, Girolamo Cardano, had a problem that mathematicians at the time were trying to, figure out. And it turns out imaginary and complex numbers were how he was able to solve this problem before anybody else that we know of anyway. Right? So extra credit opportunity right there if you have me uh, for Algebra 2. If you have any questions over imaginary numbers, it's pretty straightforward, but if you have any questions over it, shoot me an email or come and see me. Goodbye.